The objective of this experiment was to calculate the pressure drag coefficient of a circular cylinder when exposed to high velocity airflow, and examine how this drag might change when the cylinder's Reynolds number and surface roughness change. To this end, a cylinder was placed in Cal Poly's low-speed wind tunnel so that the flow and pressure over it could be observed and analyzed. Visual observations and pressure measurements were taken at two different Reynolds numbers, each produced by RPMs of 230 and 460. Flow was observed first over the smooth cylinder, and again with sandpaper on the cylinder to trip the flow and create a turbulent boundary layer, hopefully causing it to stick to the cylinder longer. After collocating the measured data and visual observations, it was clear that increasing the surface roughness of the cylinder created turbulence in the boundary layer and caused the air to stick to the cylinder for longer as it flowed around it. Through our experimentation, we are seeking to quantify the effect a turbulent boundary layer will have on drag. This is a method of passive boundary layer control. Golf balls take advantage of this effect using dimpled surface to control the boundary layer during flight. The dimples trip the boundary layer close to the leading edge of the ball, causing the rest of the boundary layer to stay attached to the ball longer. This culminates in an enormous increase in potential range across all club swinging forces. Golf balls are one of the many applications of controlling the boundary layer of objects subjected to flow. Airfoils work in the opposite way of golf balls, being designed in such a way so as to keep the boundary layer laminar from leading to trailing edge, minimizing turbulence.
For this experiment, we used Cal Poly's large-scale wind tunnel to produce the desired airflow. In the middle of the test section was placed a 14.6-inch diameter plastic cylinder that spanned the width of the tunnel. To help visualize the flow, both the laser sheet and Ryobi LED lights were used to illuminate the smoke produced by a liquid smoke machine as it flowed around the cylinder. Lastly, we tripped the flow around our cylinder using medium grit sandpaper attached to the cylinder using aluminum tape. Before recording data, the ambient temperature and pressure were noted. They were 18.1 degrees Celsius and 1012.5 hectopascals, respectively. 90 minutes later, at the end of the experiment, the temperature had dropped steadily down to 17.2 degrees Celsius, but the ambient pressure had the same value despite deviating approximately plus or minus 1 hectopascal during the experiment. Over the course of the experiment, weather outside remained sunny and humidity was constant at 30%. To ensure the data we gather has the highest degree of accuracy possible, the following steps were taken prior to data recording. We calibrated pressure readings from SCANavalve using LabVIEW. We secured the cylinder inside the test section. We checked pressure ports for any blockages. We positioned the smoke machine just before the tunnel inlet to inject directly into the free stream. We double-checked the test area for debris inside and outside the tunnel. And lastly, we ran through the safe working procedure. Each dataset was taken with SCANavalve and included 100 data points taken at a frequency of 44.4 Hz. Simultaneously as the first set of data points were being recorded, the ambient conditions in and out of the wind tunnel were measured. The first few runs of the two chosen wind velocities were conducted with no material on the cylinder, or in other words, were not tripped. The wind tunnel was set to 230 RPM, or 10 meters per second, and at the same time the smoke machine was activated to produce an easily visible streak line. After allowing the wind velocity to stabilize at 230 RPM and repositioning the smoke machine for the ideal streak lines, various pictures and videos were taken to record the visual effects the cylinder affected on the airflow. Next, the wind tunnel was increased to 460 RPM, or approximately 20 meters per second, and the process was repeated, with several more pictures and videos taken to document the visual characteristics of the flow. After observing visually the flow at 460 RPM, the smoke machine was turned off, a clearing period of about 2 minutes was allowed, and then pressure measurements on the cylinder were taken using SCANavalve. 2 sets of pressure data were taken, the wind tunnel was slowed down to 230 RPM, allowed to stabilize, and then 2 more data sets were taken at this speed. After the first run of measurements and observations, the wind tunnel was turned off completely so the cylinder could be modified. It was decided to trip the flow by attaching several strips of sandpaper approximately 6 inches long to the front half of the cylinder using aluminum tape. 6 strips were used to cover as much area as possible on the upper front half of the cylinder. After ensuring the sandpaper was as secure as possible, the wind tunnel was secured, the safety working procedure was followed, and the exact same process was repeated as before, with both visual observations and pressure measurements being taken at the same air velocities in the same order.
The coefficient of drag obtained from running flow at 230 RPM over the cylinder while untripped was 0.88439, which was along the lines of what we predicted would happen. This is because the flow was not moving with high velocity, causing little turbulence in the boundary layer and therefore causing vortices to form very rapidly after passing over the cylinder and creating a high amount of drag. At 460 RPM flow over the untripped cylinder, we obtained a coefficient of drag of 0.79649. This just about met our expectations as well because the flow was faster, causing a more turbulent boundary layer than before and causing the flow to separate later than at 230 RPM. Next, we obtained a coefficient of drag of 0.90032 when running the tunnel at 230 RPM but using flow tripped by sandpaper. This was higher than we expected because it ended up to be a higher value than the untripped flow. This anomalous result could be explained by measurement error, as there are probably no real differences between the two scenarios when running at low speeds such as 10 meters per second, which is the wind speed produced by running the tunnel at 230 RPM. The final coefficient of drag calculated was at 460 RPM, which ended up being 0.49753. This met our expectations as it was much lower than all the other calculated coefficients. This is due both to the higher speed and the fact that the flow was tripped by sandpaper, causing more turbulence and making the flow separate later in its path across the cylinder. Since the flow separated later, the vortices and disturbances caused by flow separation occurred farther away from the cylinder and the total drag was smaller. In our plot of the untripped data, the coefficient of pressure seemed to not stick closely to the theoretical plot that we generated until it reached an angle of around 300 degrees. This shows how the coefficient is slightly higher during free flow at 460 RPM, but when the flow begins to curve around the cylinder at around 300 degrees, both the 230 RPM and 460 RPM runs had the same coefficient of pressure. The value peaked at around 1 and may have gone a little over 1 in our calculations, but I believe this may just be due to the nature of the pressure probes not being perfect measuring tools and us not having time to perform multiple runs of data collection. The reason it reached its highest point toward the trailing edge of the cylinder is because with laminar flow, it took until that point for the boundary layer to reach a state of turbulence. When we plotted the tripped data, it stuck more closely to the theoretical curve than the non-tripped data, but it still wasn't perfect. The flow at 460 RPM followed the predicted curve closely until about 90 degrees, then behaved roughly in the same manner as the 230 RPM flow. Overall, the coefficient of pressure was higher for the flow at 230, but it fluctuated between the two speeds between the angles of 90 and 280 degrees. During the runs with the cylinder flow being tripped, the coefficient of pressure value fluctuated much more than when the cylinder was bare. This is due to the trip causing much more turbulence around the cylinder, causing the amount of pressure exerted at any given point to change.
One of the main sources of error we encountered during experimentation is tainted measurements from our pressure ports due to the smoke machine. Injecting smoke into the flow is a great way to visualize the effect the cylinder has on the free stream for vortex shedding and the wake as a whole. Unfortunately, a number of experiments were run before us using the same rigging as ours. This means the pressure ports positioned around the cylinder's circumference were exposed to an excessive amount of smoke beforehand. Therefore, within the pitot tubes, there is a significant amount of residue that will influence the pressure being measured and recorded by the scanning valve. Although this means the pressures we recorded vary from the true pressures, all of our readings were taken under these conditions, minimizing the relative error in our dataset. It would be difficult to quantify the smoke's effect on pressure readings precisely, but we are confident in the conclusions drawn from the dataset we gathered. All of the readings have the same offset due to the buildup, which keeps the error from compounding over successive runs. Other less significant sources of error that likely affected the results of this experiment include slight variations in the ambient conditions, like slight pressure variations and a 1 degree drop in temperature over the course of the lab, doors to the wind tunnel being opened several times during testing, slight inherent error in our measurement instruments, and a tour group coming into the wind tunnel during our last data collection period. Each of these sources of error influenced the data to a certain extent, but none great enough to prevent us from reaching our conclusions.
We successfully confirmed that having a turbulent boundary layer in the flow over a cylinder significantly decreases drag. Using our trip strip of sandpaper, we were able to control where the boundary layer separates from the cylinder's trailing edge. Although our experimentation was focused on creating a turbulent boundary layer, the concept can be extended to any scenario where the certain flow characteristics are undesirable. For instance, aircraft wings are designed to keep the boundary layer laminar to minimize turbulent forces that would otherwise cause instability. Boundary layer control is common in all areas of aerospace design, as it adds a much larger degree of authority over an object's flow attributes.